Back. Problem 3. Find the area of the region between the curves y equals x and y equals cube root of x. Alright, we don't have pictures, so we need to draw some pictures here. To find area between the curves y equals x and y equals cube root of x. So, we have pictures here. Here is cube root of x. And here is the line y equals x. Alright, cube root of x and y equals x. So we want to find area between these two curves. Alright, you notice they are both odd functions, so there is a symmetry here. If you like, you can say take this area and double it. So all you need to do is find the first area. Okay, either way, we need to find out these intersection points. In other words, to identify the intersection points, we write the two expressions equal, right? Cube root x equals x. Cube both sides. Cube of cube root is x equals x cubed. Get them together on one side. X cubed minus x is 0. Get x common. X squared minus 1 is 0. Continuing factoring, you get x times x plus 1 times x minus 1 is 0, which fetch us x equals negative 1, 0 and positive 1. Corresponding to these, the intersection points are, notice you could use either this expression or this expression. X equals negative 1, y will be, you see, y could be, you could use either of these expressions and equations and you'll get the same answer. When x is negative 1, y is negative 1. When x is 0, y is 0. X is 1, y is 1. So these points are negative 1, 0, 0 and 1, 1. Now, over the interval negative 1 to 0, so when x is negative 1 until 0, x is above cube root x, whereas from 0 to 1, cube root x is above x. Alright. So the required area is negative 1 to 0. Over this interval, x is above cube root x. So x first, cube root x next, plus 0 to 1, cube root x is above x. That's your expression. Now it's a simple matter of finding antiderivatives. Alright, this is standard material. You take antiderivatives, evaluate at the limits. Notice 0 is unnecessary because substituting 0 fetches you 0. All you need to do is substitute 1 and negative 1. Okay, 1 is this and with the negative 1 is this. All right. Finally, the answer I get is 1 divided by 2. 1 by 2. All right. Next problem. Likewise, find the area of the region between the curves y equals sine x and y equals sine 2x over x equals 0 to pi over 2. Again, we need graphs. All right. Y equals sine x, y equals sine 2x. Now, from 0 to pi, sine x looks like this. And sine 2x goes through an entire cycle. Now, the question is not over 0 to pi. The question is from 0 to pi by 2. So 0 to pi by 2. So all I need is this region. So if you notice, I need this area plus this particular area, a small area here. So that plus this. Before that, I need to know the intersection point. Find the area from 0 to pi over 2. We first find the intersection points over that interval. How do I get intersection points? Sine 2x equals sine x. So we basically use the two expressions for y and set them equal to each other. Sine 2x is 2 sine x cosine x. So that is equal to sine x. Bring that sine x to the left hand side. You get 2 sine x cosine x minus sine x equals 0. Notice sine x is a common factor. So 2 cosine x minus 1 is 0, which fetch us sine x equals 0 or cosine x equals half. So you need to find values of x over the interval 0 to pi over 2. Sine x is 0 when x is 0. Cosine x is 1 over 2 when x is pi over 3 in this interval. All right. So over the interval, 0 to pi over 3, we have sine of 2x greater equals sine x. How do we know that? Go back. So that's the first intersection point. So from 0 to the first intersection point, sine 2x is higher than sine x. Between pi over 3 and pi over 2, sine x is higher than sine 2x. So in the second part, you have sine x greater equals sine 2x. In the first part, sine 2x is greater than or equal to sine x. So to find the entire area, you have to break up the area from 0 to pi over 3 with sine 2x first, sine x next, plus pi by 3 to pi over 2, sine x first, and then sine 2x. For ease of calculation, notice these are essentially opposite expressions. So let's understand this particular integral. Sine 2x minus sine x. Sine 2x is 2 sine x cosine x. Sine x is sine x. Get the sine x out, you get 2 cosine x minus 1 dx. Now you may use substitution. Set u equals 2 cosine x minus 1. Then the differential du is negative 2 sine x dx. Dividing by negative 2, I get negative du by 2 is sine x dx. Which means this integral now, right, equals 2 cosine x dx minus 1 is u. Sine x dx is du over 2 with a negative. So this integral by substitution is this integral. When I take the integral of u du, I get u squared by 2. This is this is an indefinite integral, so I have a constant here. In other words, overall, I have replacing u by 2 cosine x minus 1. I get negative 2 cosine x minus 1 squared over 4 plus a constant. Therefore, my original integral 0 to pi by 3, if you recall, this integral, right, is simply the, after computing the antiderivative at the limits pi by 3 and 0, plus this is the opposite of this. So notice I'm going to have a negative because of the opposite, but my antiderivative already had a negative, so it's an overall positive with these as the limits. The rest is careful calculation. Remember, cosine of pi by 3 is half. 2 times half is 1, minus 1 is 0. So this expression fetches me 0. On the other hand, at limit 0, cosine of 0 is 1. So 2 minus 1 is 1. Squared is 1. So that gets me 1 over 4. Here again, cosine of pi over 2. Cosine of pi over 2 is 0. So that gets me negative 1 squared. So that's a positive 1 over 4. The last one, cosine pi over 3 is half. 2 times half is 1, minus 1 is 0. So that fetches me a 0. So overall answer is 1 by 2. All right. So next problem will continue in our next video.